All right. So today's lesson is going to be one on z-scores, and z-scores tie into everything else we've done in this introduction to statistics unit. So very basic, a z-score is a way to standardize our data to understand a data point in relation to its data set. And so very specifically, what a z-score tells us is in your data set, in your distribution, how far does a specific data point or observation fall from the mean? And when we say how far, we really mean how many standard deviations. So we want to fill out the sentence here. For an observation and a distribution, this value shows us how many standard deviations the observation is away from the mean. So this really falls hand in hand with the other information we have looked at over normal distributions, finding the mean, finding the standard deviation, and we've looked very specifically at those cutoffs of how far away, what data point or what number would be exactly one standard deviation, two standard deviations, or three standard deviations above or below the mean. The z-score allows us to look at any of our data points and determine how far is it from the mean. That also, as we look down here later, would help us know which of these different cutoffs would it end up in. So because a z-score is just it's telling us how far away the data point is, it is a standard deviation. So therefore, it doesn't actually have units. So z-scores never have units. If our z-score is positive, that means that it is above the mean, our data point's above the mean. And if our z-score is negative, that means that it's going to be below the mean. So if you want to box those two. All right, and so one of the reasons we use them is that it allows us to compare scores on different scales. So one of the examples we're going to look at is the SAT and the ACT. So those are scored, the ACT is only up to 36 versus the SAT, we get our scores in the thousands. And so we want to be able to compare how did you do relatively on those assessments. And so the z-score is something that is going to help us determine how well did you actually do compared to your peers, even when your raw score looks so vastly different. The way that we end up finding our z-score is using this formula right here. Now, we've been using these symbols a lot. We know that x represents the actual data point, so the value that you're looking at. Mu is your mean, and lowercase sigma is your standard deviation. So in order to find this, we're always going to do your data point minus the mean and then divide it by the standard deviation. All right. So if we keep scrolling, we can kind of look at this here. As I mentioned, z-scores are highly related to normal distributions. And when we put the two hand in hand together, we get what is known as the standard normal distribution. This is a very specific type of normal distribution. It is a normal distribution when the mean is 0. So the mean of your data set is 0. And the standard deviation is exactly 1. In this case, when this is the case, that means our horizontal axis down here are the z-scores. So if we look at this, and this has everything we've kind of talked about on it, this is our normal curve. Inside are the percentages for the empirical rule. We know that if our data is truly normal, then the percent of data that falls within one standard deviation on either side is going to be 34 for a total of 68%. This also going to help us find our percentiles. We've talked about that a little bit as well. But we can figure out what percent of data falls here. We know this is around 0.13 or 0.15%. So anything here would be at the 0.1%, which would be almost even less than the first percentile. So you see we have those going along as well. What's cool here with the z-scores is that if my mean is 0 and my standard deviation is 1, well, 0 plus 1 is just 1. 0 plus 2 is just 2. 0 plus 3 is just 3. And so the numbers that would end up here actually would be the z-scores. So in a case like that, if this were my data, if my mean were 0 and my standard deviation were 1, and I knew that I had a value of 2, that would mean that I was 2 standard deviations away, and that my z-score would be 2. So this just gives you an idea of what those z-scores mean, especially as we go to interpret them. So say that something had a z-score of negative 0.89, well, then we know that that number would actually fall kind of here. This is how far away from the mean that it would be. We know that it fall into that major amount, the 68%, and it's almost one full standard deviation away. So just a way to interpret this a little bit better. So let's go ahead and do an example here. So here we want to compare how you did on the ACT versus the SAT. So it says you got a 27 on the ACT and a 1900 on the SAT. You want to know which test you did better on so that you can submit that score on your college application. So in order to do this, what we need to do is we need to determine the z-score of each of them. So let's come here with the ACT. We're going to do your value, so 27 minus the mean over the actual standard deviation. That's how we go about doing this. Now 27 minus 21 is 6 over 5, which is approximately or exactly 1.2. So for the ACT, my z-score would be 1.2. Now if I come over here and do the SAT, we're going to do the same thing. My score was 1900. So we're going to do 1900 minus the average over the standard deviation. When I do that, I get 4 over 3, which is approximately 1.33. Oh, interesting shape there. So even if we just come over here, we can see immediately a 27 is greater than a 21. So we did better than the average on the ACT. A 1900 is greater than a 1500. So we also did better than the average on the SAT. But honestly, looking at this, I'm going, okay, 21 to 27, that's a, 6 whole points. 1900, 1500, 1900, that's 400 points. So 6 versus 4, my gut instinct would have said I did better on the ACT. But looking here, what we're really trying to see is how did you do compared to your peers? And that's where the standard deviation and the mean come hand in hand. So if I were actually to answer this problem altogether, I would say something along the lines of, because 1.33 is greater than 1.2, it means, compared to my peers, I did better on the SAT. I'm more standard deviations away from the mean on the SAT than I am on the ACT. On the ACT, I'm only 1.2 standard deviations away. So if we were to come up here and kind of put this for the SAT, I'm going to go back to this. To the ACT, I'd be about right here. But for the SAT, I would be right here. And we know we want to be, when we're trying to compare test scores, we want to be the furthest away from the mean. That's the most outstanding we can be. So because 1.33 is going to be further on the z-score scale, I know that means I did better comparatively. All right, I'm going to do one more of these with you guys all together. We're going to kind of put some different parts together. So here's another example. It says in Mr. Brady's stats class created a dot plot of their heights in inches. The figure below shows the dot plot and the summary statistics. Brent, a student of the class, is 74 inches. I'm just going to go ahead and find him here. Brent. This is who we're comparing. How tall is Brent compared to the rest of his class? Notice here the problem wants us to use both a percentile and a z-score to answer this. When I color code those, we can go back and do them in the different colors. So if we start with the z-score, that's one we've been practicing. He is 74, that's his data point. I'm going to use the table here. I see that my mean is 67. And I see that my standard deviation is 4.29. When I put this all on my calculator, I get a z-score of 1.63, which means he's actually pretty far above the mean, 1.63 standard deviations. In order to do the percentile, remember the percentile is what percent of people scored less than him. So if I look at this, the total number were 25 students. So I'm going to divide by 25 to find a percent. 1, 2, 3 of those were him or higher. So 25 minus 25 minus 3 is 22. 22 divided by 25 is 88%. Once again, I could have gotten that 22 by actually counting up each of these data points, but in my mind, it was easier to subtract him and everyone higher because there were less of them. So if I were to fully answer this question, we would say Brent, being in the 88th percentile, is taller than 88% of his classmates. Furthermore, his height falls 1.63 standard deviations above the mean. And that is how we can use this to go ahead and compare Brent to his classmates. Notice, even looking here, we can use common sense. Obviously, 74 is greater than 67 to know that he is above the mean, but also, once again, it was a positive z-score, which is what put him on the top. Problems, though, always like to be a little tricky, so this one is slightly different. It says Brent is also a member of the school's basketball team. The mean height of the players in the basketball team is 76 inches. On the basketball team, his z-score, make that orange, is negative 0.85. Hold up right there. This is our first time seeing a negative one. That means Brent's height of 74 inches is actually less than the mean, which makes sense. We know that 74 is less than 76 inches. So that's just being able to look at the z-score. We automatically know that his height is less than the mean because it is negative. The question is, what is the standard deviation? So in a problem like this, I'm going to go back to my formula. X minus mu over sigma equals z. Well, I know that my x is 74. That's how tall he actually is. The mean is 76. We're trying to find sigma, and we know the z-score is negative 0.85. So at this point, it's just solving. We know anytime we have something in the denominator, we swing it up to the other side. I'm going to go ahead as I do that, subtract here. So that gives me negative 2 equals negative 0.85 with the sigma hanging out. So in order to get sigma, we're just going to do negative 2 divided by negative 0.85, and that gives me a standard deviation of 2.35, which would represent inches in this case because we are talking about heights. So just another way that we could use the formula. So at this point, I'm going to leave you guys to actually try this problem on your own. For those following along with your worksheet, this is actually on your worksheet, and I will have it posted on my page for you to check yourself. But this is some really good practice to go along with how do we find a z-score and what can we do with that.